So a very good morning once again. And this time we're going to cover the basics of computer organization and architecture. And we'll also look through the programmer's perspective in terms of programming the hardware and then programming the software. Okay, I know in our last class, I made mention of hardware programming, where we have to deal with the hardware description language. And we actually have two types, the Verilog and the VHDL. Well, it is believed that Verilog is simpler to code than the VHDL, but we most likely will go with the VHDL because it's an IEEE industry standard language for both simulation and synthesis, okay? And if we still have some time before your exam, we may want to play with a few things. But just before then, I would love to share this screen. Trust you can see this. This is Model Sim. So you want to install the Model Sim application on your systems, maybe before our next class. And here, this is a sample of a VHDL code, okay? So, which stands for Very High-Speed Integrated Circuit Hardware Description Language. And I know we have some FPGA boards on campus where you may be able to, play with some of these things in terms of designing, or better still, relating with reconfigurable systems. Well, be that as it may, we'll be looking into this and, if possible, designing a few or programming a few hardwares where we are able to, rather than draw our logic circuits on paper, then the instructions performed by those logic circuits could be coded. That's what we mean, okay? So we could run some lines of codes and then achieve the activities where we have to deal with the input, then the output, and all of that. And the beautiful thing about the VHDL is that it is quite structured, okay? And if you've played with other programming languages, which has to do with your software programming, then this shouldn't be a problem, really, because although now we just have to deal with what's it called now? Hardware programming, okay? So I think that is it. I just thought I should make mention of this. So you want to install Model Sim in your systems, and then we'll take things up from there, okay, in our subsequent lectures. So we are able to probably relate with a few details. And just a run through for the VHDL system, let's say the design unit, you'll observe, let's see, I can scroll. It's just, so let's go back to our slide, our lecture slide. Okay. Can you see the slide?
Yes, sir, we can see it.
Okay. So like I mentioned earlier, we're going to be dealing with
Sorry, sir, we can't hear you very well.
so can you hear me now? Can you hear me very well now?
Yes, yes, I better now, sir.
Okay. So, well, I just want to jumble a couple of details here, so we'll move on. Computer architecture and organization. That's okay. Now, we've actually related with circuit designs and all of that. Beautiful. And we know that in your computing systems, we, coming from the abstraction level, we put through from, we control from the logic gates. So from the logic gates, we could design our other devices. And we know for our logic gates, we have two parts to it, the combinational circuits, and then we have the sequential circuits, right? Now, these you have covered in different lecture series, okay? So we don't want to go into details again because of time. We don't have the luxury of time anyway. So we know for your sequential circuits, we do not have no memory, right? But so all we get to deal with are the gate devices, right? Gate devices. Now, for your sequential circuits, we have memory. But the point is we use our combinational circuits to arrive at the gate devices. And here we have flip-flops, right? And with the flip-flops, we could design your registers, okay? So it means that the register, although it is a sequential circuit, it is designed using combinational circuits, right? Now, we have your arithmetic logic unit. Now, your arithmetic logic unit is strictly designed from combinational circuits, right? Then we have your others, which we could put together to design your arithmetic logic unit, okay? So we could put up your other, your AND gate, your OR gate, and even the multiplexer, okay? So once we put them all together, then we could design an arithmetic logic unit. Say we have the AND gate here, we have the OR gate here. Let's say we have an adder here. So let us wipe this. Just trying to put through things you already know, okay? Yeah, based on courses you already took. Yeah, then let's say we have our multiplexer here. This is a MUX, right? Then say this is our adder. So if we have, say, an input A and another input B, then we intend to get our result here, for instance. Then we could perform an operation here. Let's say operation here. Then this could strike through all the way, where we have carry in here, and then carry out here. So our input can come in this way, right? And then also this input A, for instance, can be fed into our OR gates, and then also so the other, right? Then the second input to the OR gate can equally be connected, or the AND gate rather, can equally be connected to the OR gate, and then we have it here to the other. So let's wipe this, for instance, that's the B. Okay, so this goes to the 0 value, then this goes to, sorry about this one, right? And then This is 2, right? So let's indicate the arrows. So, well, this is simple ALU, okay? And then we know the operation here is a two-bit value, and then selects, this selects the operation, that will result in the result. Because for your MOS, we have the inputs, multiple inputs, and then we have a single output, then we have the select button, okay? And the select button here is performing this operation. So looking at this, we know that your multiplexer itself, your multiplexer is strictly combinational circuit. Your adder is strictly combinational circuit. Then the gate devices, your AND gate, OR gate, and all of that, NOT gate, they are all combinational circuit devices. So we know that if you want to design a computing system, for instance, the arithmetic logic unit of that computing device will be designed and fabricated physically in terms of the hardware implementation using combinational circuits. I think that's where I'm going to, okay? And then we know that we'll definitely have, the CPU, where the register will be resident in and all of that. We know for us to design our registers, we need to make use of sequential circuits, okay? Flip-flops, for instance, okay? And your counter is just the type of your register, okay? Now, these things we've talked about, so we could pull these things together to design a single computing device. And we already know that a small microprocessor could contain millions, hundreds of millions of gates. So if we want to begin to put those gates together one by one, that would be too cumbersome. And one simple way to go about the design would be to write codes using the hardware description language. So we could just navigate through some of these things, using some lines of codes, and then we're able to achieve our results rather than draft all of this, rather than put all of this together. I don't know if you get what I mean. Are you with me, please?
Yes, sir.
Yes. So that's the essence. That's the reason for our hardware description language. Okay. Language, the HDL. Okay. So I'm sure some of you want to begin to learn one of those languages now, especially those of you that want to major in electronics, in electronic design, you want to go into integrated circuit chip devices and all of that. So you want to concentrate now. I know some of you are interested in the soft solution programming, like programming languages like C++, C#. Then some of you are running to Python, React, and all of that. It's beautiful. Okay. Now, for those of us that really want to advance the frontiers of electronics and its integration, looking at the dimension, the world is gradually tilting to electronic integration, IoT sensors and all of those stuff, nanotechnology and all of that. So you want to go into, you want to pick up the VHDL. It's a powerful tool, and then with the model sim, you really don't need a physical board. So you could play with it and then get going. And one thing I want to mention here is that just like all programming languages have, their design framework. So for the VHDL, which we already said is a very high speed integrated circuit hardware description language. The core design units are entity, architecture, configuration, and package. Okay. Oh, sorry. I just wrote page. So I was not writing what I was thinking. You don't want to do that in your exam. Package. Yeah. Okay. Okay, so I think let me just introduce this quickly before I jump into the next thing. Okay. Okay. For your hardware description language, so we are taking VHDL, and we said the design units, so that when you open up that interface, okay, so the design units we have are entity, I already mentioned that, and this is used to define the external view of the model, right? This defines the external view of the model. So we look at it as the symbols, right? The symbols. So this is what the outside world sees. Now, then the architecture, sorry. This defines the functions of the model, okay? It defines the function of the model. So in this case, we'll begin to deal with the schematics, okay? While programming. Then the next design unit here is the configuration. Okay, and this is used to associate the architecture and the entity, okay? So in the configuration aspect, after we've given details about the entity, the architecture, now in the configuration, we want to associate them, we want to pull them together, okay? Associates the architecture. Entity, okay? So, but and one thing you should know also is that the VHDL language allows multiple architectures to be associated with a single or the same entity, okay? And then we have package. The package. So this has to do with the collection of information that may be referenced by VHDL models, like the libraries, okay? So collection. Model. So talk about the libraries, right? Okay. So this package usually consists of two parts, okay? We have two parts to it. We have package declaration, and also we have package body. Okay. So, well, nothing to worry about, okay? You don't need to begin to freak out right now, because we'll play with all of these things, okay? So for your entity, for instance, we talk about the entity declaration. So when you want to declare, it's more like, okay, you want to declare XYZ in your C# or C++. What do you do? So it's the same philosophy, the same idea. Okay, so all designs are created from entity. That's where we start from the entity. So it goes down to architecture, then the configuration brings these two together. Okay, so I want to design a register. So I know I'm going to have quite a number of combinational circuits in there, but this design should be able to hold data or instruction at some point in time, so it should have a memory. So what are we going to do? So those components that we're going to put together, And then we now have to come to the declaration. How do we declare the entity, even the architecture? Then how do we go about the configuration? So for instance, I'm digressing right now. This is not what I intended to talk about today, but so let's say, okay, the entity declaration. So you're going to have something like this entity, then we're going to put the entity name, right? Then we're going to say is, the entity name is. Then under this, we have two declarations to make. We have the generic declaration. Talking this VHDL now, okay, VHDL program. Then we have the port declaration, okay? Then we say and the entity, okay? And entity. And once we say you should end the entity, then we have to include the entity name, right? That's it, okay? Now, this end entity is kind of selective. We use it for the VHDL version from 99 till probably newer models, but you could just say end. You just put simply end for all versions, okay? That's supported by all the versions of VHDL. So the point now is here we have, this is what it is. So we now know that every other thing is going to fall into this, okay? So in between this entity and end entity, we are now going to declare all of these. Then we have other things to also deal with. So what is the generic declaration? What is the port declaration? Okay. Now, when we talk about let's start with, okay, let's do the generic declaration first. So when we talk about the generic declaration, for instance, there are values that can be passed into the entity at compilation time, okay? So they are used to make the entity parameterizable when designing hierarchically, for instance. So the generic entity itself is contained inside the entity declaration, okay? So let's assume I want to do this, then in between the entity, so this is entity, you know, I've given it a name, okay? What do we call this now? Say CPE computer, for instance, is then generic. So we say generic. So here, once we put that generic, we have the bracket, and then we are going to close the bracket somewhere here with a semicolon. Okay? Then underneath this is our port declaration. Then end entity. End entity. Then here our CPE computer, right? For instance. Let's just leave this way. Now here, we are going to design some constants and put in some default values and the likes. And also, for the port declaration, we use this to describe the input-output to the entity after the generic declaration. So we have defined some constants here. For instance, then for the port declaration,
we were not used to find files. Then right
so for the port declaration, just as the name implies, port, we use this to describe the input and the output to the entity after the generic declaration, okay? So let's assume I want to design a multiplexer, okay? I know I'm going to have a number of inputs to this. then I'm going to have a single output, then I'm going to have a select port here, okay? So the port declaration will help us define all the input output to the entity, okay? So it starts with the keyword port, okay? Here, recall the keyword here for the generic declaration is generic, while for the port declaration, the keyword is port, okay? So we say port, then with a bracket, then another bracket close, then semicolon before the end entity, okay? And here, we now want to define the signal, say signal, then probably we have the clock, we have clear, then we say it's input bit, right? Then just the way you use double slash for comments in your regular programming, in this case, our comment is dash dash. Well, this applies for Verilog anyway, this double slash. Then we could say dash dash, then it means we are putting up a comment, okay? So we could say, well, the signal is in this case is assumed and it's usually not required anyway. And then we now say, well, let's say this is my output Q, okay? So I have my clock, my clear, you know, as my input here. Then I can now define my output, say Q, or say V. Let's just or Y. We'll be using Y. So let's say Y. Let's say Y. My output here is Y. So I can now say Y is my output, right? It's my output bit. So on and on, that's how it goes. So from this, then we can now move on to begin to, now you see that I use in, I use out, in for input, out for output. We have some other, you know, data types here, in, out. Then we also have the buffer, okay? So for the in, out, that's bidirectional. So in, out can only be used for both input and output. Why for buffer? Buffer is for output with internal feedback. So you really want to use that, except there's a special use, you know, you are so certain you need that in your design. So you now see that, fine, this is the hardware we want to achieve, but using your VHDL coding, we could put this up as a code, and then voila, we get what we are doing. That's the essence, okay? So from there, you can now come to the architecture, which describes the internal logic of to the model, okay? So this particular logic, we now have to define it in the architecture, you know, on and on. And then in that architecture, well, just the way we have all of these keywords here, we also have that, you know, for the architecture, in terms of declaring the architecture, the word architecture, you know, we say architecture, then put up the identifier architecture of this entity name, okay? So, and then you now tell what exactly you want. We are designing a MOS, okay? So we now begin to link up all of these interfaces, how the input and output relates, okay? So I think that's it. And let's just look at a simple example where all of this,
Thank you.
where all of this fit in. Where all of this fit in. So, well, if we have some time, we'll go back to our model sim and then check this out. So I just want to design a simple multiplexer, okay?
So,
Now,
sir, did we comment out the signal, or what exactly did we comment out under the ports?
No. I just put this. We are not commenting out the signal. It's just a comment. Probably you want to put a comment here, you know? I just wanted to tell you.
Okay, in between the signal and the output bit.
What's that?
I said, is the comment in between the signal and the output bit?
Yeah. I just wanted to, it could be here. We could put comment here. Okay, I just wanted to explain to you that, well, in VHDL, we use the double dash as to comment out. We also comment out using / asterisk, then asterisk /, or we use the dash. These are the two ways we comment things out in VHDL.
Okay, sir. Thank you, sir.
Yeah, you're welcome. So usually you just put your full column here, and that's it. Okay. But is it that none of you have any background in terms of VHDL coding? Because I know some of our lecturers get to do that with their students. I don't want to believe that, except, or let me assume you are yet to take the course, because I'm very certain Dr. Mohammed does that. He has some Xilinx or Altera FPGA boards, and some students.
In year 5.
Okay, in year 5. Okay, and you guys are in year 4. Okay, that's understandable. Okay, now we just begin the process. Okay, because this will just it's a bailout for us to quickly run through the design of especially hardware programming. We really do a whole lot of stuff. Okay, let us let's look at this. Just a simple example I pulled up somewhere. So well, we want to design a multiplexer. Okay, so in this, say we have input A, input B, and then we have the select button here. We have input A, we have input B. Okay, and then we have output X, output Y, and then output Z. Okay, where each of these happens to be a multiplexer, right? Where this is X, and this is A, this is B, and then this is select button. And this again is another multiplexer, A, B, and then this is select button. And this is Y. And here again, we have another multiplexer. And don't forget, multiplexers can be used to design your arithmetic logic unit, right? The A, B, then select, yeah? So let's say this entire design is in some block model. So this is a complete square here. Let's say this is more like the architecture of what we want to design, okay? So at the end of the day, the hardware we are going to prototype is something like this, okay? So in VHDL, we already said we have about 4 design units, the entity, then we have the architecture, the configuration, and the package. And the package, we define the libraries, right? Okay, so let's exclude that now. So let's say entity, we have entity here, okay? So we just want to put everything together here. So if from the entity, we now want to design this, then we know we are going to give a name, okay? A name to this, a name to whatsoever we want to do. What's going to be the name, okay? So let's say XXX underscore P, for instance, then is. Then we define the port, okay? So in this case, the input ports are A, B, and select. So we have A, B, comma, select, full colon. They are the input bits, right? Input bit, semicolon. Then we also define the output, X, Y, Z. Then they are the output bits. Then now, this is critical. The last line here does not need a We can close this up with a semicolon. Then remember, we have to end our entity, end entity. Then our name is SS_P. Then we now come to the architecture, okay? Then keyword here is still architecture. Then is the logic of the entity name, XXX_P, for instance, then is, then begin. Let's begin. Begin. Then say, let's put a comment here. Say a simplified model. Okay, for instance. Then our input X is less than equal to A, and it's a complement, right? Not select or B and select. Okay, so we want to put up a conditional statement now. So let's say conditional, this a comment, conditional statement, for instance. We now say our Y is less or equal to A when select is the same as 0, else B. Okay, so we can now go on to say with cell SEL being select Z is less than or equal to A when 0, comma, B when 1, comma, or 0 prime when others. So here now, I'm supposed to end the architecture. I already ran out of the line there. So let's just put it here. So this continues from here, then we end architecture. And architecture here is called logic. So call it logic. It could be SAM, okay? Semicolon. Then configuration. So we now say configuration again, that's the keyword, configuration. Then now we have to assign this configuration to the name of the entity. So we are looking at the configuration of our entity. So let's just say, because we need, the configuration needs a name. It could be anything, but for ease of identification, XSSP com, for instance, of, recall that we are, the configuration associates the architecture with the entity, right? So, but for now, we say the configuration of our entity. What's our entity name? XXX_P, then is for our architecture name, logic, then N4. Then we can say end configuration. Well, it's actually very interesting. Then configuration of our configuration name, XXX_P_com. Now, there's something I actually want to mention here, okay? because you see that our configuration here already associated our architecture with the entity, okay? And so we're able to put through and all of that. Well, this is just one off, but well, this is just on paper. So we still have to walk around playing with this, looking at a couple of examples, designing a few stuff on the model scene. So to make things a little more interesting, I'll suggest that we all have the model scene installed in our systems. And let's see in our subsequent lectures after the mid-semester exam, we could look into this, you know, by playing with one or two or more examples, okay? Now, that was a little digression into hardware description language, okay? Which is a little off our deal for today. But let's quickly go back to what we intend to talk about. Now, we know that all of these things, we have two sides to our architecture, okay? Now, before now, you were told that your architecture is your instruction set architecture, right? Which you have to now deal with. But now, we are going to see another aspect of your architecture, which we just played with using VHDL or your hardware description language, which is your hardware system architecture, okay? These two aspects, this with your computer architecture, okay? Yeah, but I know you guys get to dwell more on the ISA, okay? Okay, now let's quickly move on. So when we talk about basic computer architecture and organization. So now let's come back to what you guys already know. So we know that computer architecture deals with the design of a computer, right? So let me get your feedback before I just go on talking. So what do you understand about computer architecture and organization? Quickly, please. Yeah, we have exactly 1 hour to be out of our class.
Yes, sir. So it is basically like the way different components of the computer is organized. So like looking at like the evolution of
which are you telling me? Is it the organization or the architecture, or are they the same from your point of view?
Architecture, sir.
Okay.
Architecture first.
Okay, go ahead.
Yes. Yeah, okay, so looking at the architecture, like there are different ways like you could do like the way your data and your instructions are being collected. And architecture is like the different ways that you can basically configure it. Like something like the Neumann Architecture, the Harvard Architecture. So basically the different ways that you can possibly arrange how data and instruction are fetched or stored in your computer. So that's like the architecture part of it, sir.
Okay. Go ahead. The organization part.
Yes. For the organization, there are different ways. Like you could have, so it is just like a way of looking at what the computer can do. So like looking at something like risk or risk, like maybe you want the computer to be simplified, maybe to have many different simpler units, or maybe to have one single computer that is like to have many simpler units like in the risk computer, or maybe to have like big, like in a risk organization, if that makes sense. Or maybe to have
It's risk. You just mentioned risk, right? Reduced instruction set computing microprocessor, right? Can we say
yes,
that? Can we associate that to architecture or organization?
Organization.
No. Yeah, that's architecture still. Okay, so I know there's a little. Yeah, fine. You've done so well, my dear. Yeah, well, you've done so well. Now, well, just to run through it quickly, okay, the computer architecture deals with the design of a computer. Let's put that down. Now, computer architecture, and then we have computer organization. So the architecture itself deals with the design of a computer, okay? This deals with the design of a computer. Okay? While the organization itself, the computer organization, deals with the structural relationship. Okay? Deals with the structural relationship. Okay? Now, we spend so much time trying to figure out the architecture aspect. So it's like your curriculum is built around architecture, 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 architecture. So whether we have to go hardware, software, whichever way, but the architecture itself is the programmer's perspective. Okay, when we get to deal with the computing technology itself. But let's just look at these two words. One has to do with design, and one has to do with the structural relationship. Those are two major keywords here, okay? So architecture deals with the design, the organization deals with the structural relationship. That is why in the organization aspect, we begin to talk about how the CPU, the memory, the input, output, and interface using the system bus, the data bus, address bus, control bus. That's what we talk about in organization, the structural relationship. We have the CPU somewhere. We have the memory somewhere. We have the input, output devices, the peripherals somewhere. So how are they connected together? How do they relate? Okay, so that's it, organization. Okay, you can think in terms of your class. There's an organization. Right now, even in the institution, in the department, the head of department decided to feature me as the tutor for this course this year. It could be someone else at his discretion. So, and now coming to the class, we have some class reps, right? So if I have to relate with the entire class, I don't have to begin to send messages to everybody. I want to relate with the class reps. So I get to the class reps, they get to you guys. So there's a linkage, okay? Now, if there's any other thing we need to do, I escalate back to my HOD. Then my HOD have his own line of activities too. He reports to the dean. Then the dean reports to the vice chancellor. That's organization. Do you get the point? But when it now comes to how we get to deal with ourselves, okay, now I have to send information to you. So it's either we came to the classroom this morning or we are online now. Now, I needed to show you guys quite a number of things, the software side and all of that. So I won't be able to do that in the classroom. So we all have to be with our devices so we could play with some applications and all of that. So that may now come to architecture, the design, okay? The design. And when we say architecture, in as much as it deals with the design of the computer, it also deals with the functional behavior of the system itself, okay? So it also deals with the functional behavior of the computer system, okay? So in other words, here, the architecture deals with one, instruction set, and two, we have memory addressing techniques, memory addressing techniques. Then three, we have bit representation of data. Then four, we have input-output mechanism. So these are the things you guys have actually related with in your previous lectures, okay? So while relating with the computer architecture, you have to talk about your instruction set, your addressing scheme, and we have quite a number of addressing schemes, right? I know that you guys we already taught direct addressing mode, register address mode, indirect address mode. Which other one can you help me? Register indirect addressing mode. Which again?
Immediate mode.
Yeah, immediate address mode. We have index address mode, and we have one relative addressing. Yeah, so we have quite a number of, those addressing modes, which you already talked about. Now you see all of those addressing modes and they are all part of your computer architecture, bit representation of data, input output mechanism. Perfect. Now, if your computer organization deals with the structural relationship, now is that clear? Is that clear? I need your feedback now. The computer architecture is clear. Okay. Now, for the computer organization, we already said or mentioned, or you already know that it deals with the structural relationship. Okay. And so we can also say it has to do with how the computer works. Okay. It has to do with how the computer works, right? So the organization deals with, say, one, control signals, okay? And two, the interface between the computer, memory, and peripherals, okay? Interface between the computer, memory, and peripherals. So those are the things we get to talk about when we have to talk about the organization. So now I really don't know. Which should we talk about first? Should we talk about the organization first or the architecture first? Because I know the organization is what you already know as well. Hello, class? Are you still with me?
Yes, sir. Yes, sir.
Okay, let's do architecture. Okay. Okay. Now, let's do architecture then. Now, we already mentioned that the architecture deals with the design, okay? And if we now have to play with that design, we now see that it includes the instruction set, the hardware components, and system organization itself, okay? That is the architecture. And the computer architecture is categorized into two parts, like I mentioned earlier, okay? So when we say computer architecture, we have two parts to it. The instruction set architecture and the hardware system architecture. So for the instruction set architecture, it includes the specifications that determines how the machine language program will interact with the computer, right? So this now has to do with the specification that determines how the machine program interacts with the computer, right? While the hardware system architecture deals with the computer major hardware subsystems, okay? This deals with the computer So here we have the central processing unit, we have storage devices, we have input, output, and so on. Okay. It also includes the logical design and data flow organization. Okay. It includes the logical design and data flow organization of the subsystems, right? So this is computer architecture. So let's assume we have P is the same as 6, let's say minus 4, for instance, okay? So we now have to deal with instruction set, okay? Now, depending on the instruction set architecture, we have quite a number of them, okay? So let's assume we have this instruction set where these are all tied to registers. Let's say this is now R1, R2, for instance. Then we could say move R1 to 04H location, then move R2 to 03H location. Then we say sub, that subtract R1, R2. Then we now say store P, right? In R1, okay? So we can also say the architecture could be push 04H, then push 03H, for instance, and then it now says sub, then pop P, you know. So it depends on the architecture, okay? It could use load and then add, okay? So it depends. It depends on the particular ISA, you know, that is being used. So based on the instruction set architecture used in the computer design, the hardware will be chosen. So now, if we are using this, so we know that we're going to choose these two hardwares, right? Based on the architecture. So based on what we want to do here, we want to subtract. So we do this, okay? And there we go. So this now will lead. So depending on what we have here, programmed in our system, and we now have to perform this operation, then that will now lead to the hardware that we now have to choose, leading to the hardware system architecture, okay? So that's just a general overview. So let us look at the classifications, which you already know, okay? The classifications, okay? Computer architecture classification. So now we are going to, our classification is going to be in two folds, okay? The first one will be based on the design architecture, which you know, okay, which you have been making mention of. And the second will be based on the number of processors, based on the number of processors, okay? So, and based on the design architecture, we have the von Neumann, and the non-von Neumann architectures, right? So for the non-von Neumann, we have the Harvard and the modified Harvard. Now, how about the based on the number of processors? Who can help me with that? Based on the number of processors. Okay, I think you're waiting for me, right? So we have this single instruction stream, single data stream, that is SID, okay? Then we also have the SIMD, that single instruction stream, multiple data stream. And then we still have some others. Some are really not practicable in terms of implementation. The multiple instruction stream, single data stream, that is MISD. Then we have MIMD, MD, right? MIMD, MIMD. That's multiple instruction stream, multiple data stream, okay? So these are based on the number of processors, and these are the von Neumann architecture, okay? And the non-von Neumann based on design. So now for the von Neumann architecture, you already know that it has three major subsystems, right? Three major subsystems: the CPU, the input-output peripheral, and the main memory, right? So we can have something like this, where we have the register here, the arithmetic logic unit here, the timing and control unit here. Then here, you can say we have the interface, right? Interface. So we have the input-output peripherals here. And then we have the main memory. And then this is the bus system. The system bus. Now, the system bus itself, we deal with that in the organization. And here, you see that it stores the instruction and data in the same memory location. That is the major limitation of the von Neumann architecture, because the CPU could not operate on the instruction and the data simultaneously, and we'll call that the von Neumann bottleneck. And then we have the non-von Neumann, right? The non-von Neumann architecture. So we have two sides to this. So in the first version, which is the Harvard architecture, we have the instruction, the memory, for instance, in this location. Then we have the input-output peripheral, somewhere around here. Then we have the processor. And then we have the data memory. Okay? So they are all interlinked. Those are all bus lines. And then here. Good. Now, this is the Harvard architecture. Harvard architecture. So, and in this architecture, there are separate memory units, one for storing the instruction, as we have here, and one for storing the data, as we have here. Separate memory units. Beautiful. All right. And then the processor can both read an instruction and perform data memory access at the same time, unlike the von Neumann architecture, which happened to be the major drawback of the von Neumann architecture. So computers having the architecture, where this particular architecture were faster, okay? Because the instruction fetches and data accesses they were not competing for a single memory pathway, like in the case of the von Neumann architecture. But afterwards, we now have the modified Harvard architecture, where in the processor, we now have a small cache. Okay. So this architecture now relaxes the strict division of the instruction and data memory access, okay? Because here, We now have the instruction memory and secondary data. Okay, secondary data. So we have data memory, peripheral, and all of that. Okay. And then in this architecture, the processor is accompanied by a small yet very fast memory storage called the cache, like we say it here. So when the processor is executing from the cache, it accesses a pure Harvard architecture. And when it is accessing from the back-end memory, it acts like a pure von Neumann machine, okay? So you see that in modern devices, the modified Harvard architecture is preferred. So when we talk about the architecture based on the number of processors, here we now see that for the single instruction stream, single data stream, we have something like this. We have the memory. This is the memory, right? Then we have the control here. And then we have the operate here. Then here we have instruction, the single. And then we have data here, which is also single. Then the result, definitely we need the result. And then this just relates with this. Boom. So single instruction stream, this is the instruction stream, and then single data stream. So this particular architecture is more like the von Neumann architecture or the category, okay? Then you will see that this single instruction stream and single data stream have one CPU that executes one instruction at a time, just one CPU. And here it also executes one instruction at a time. So hence it is single instruction stream. And then it also fetches and stores one item of data, just one item of data at a time. So hence it is called single data stream. Now, when you look up the single instruction stream, multiple data stream, we have something like this, something similar, okay? We have the memory. Then we have just a single control here, right? And then we have the multiple operate, then this operate here. So this is data. This is instruction here, right? Instruction. Then we have result. Then here we have data. Then here we have result. So this can either operate on this or this. So the processor arrays falls in this category, okay? And the single instruction stream, multiple data stream have a control unit that operates like the von Neumann architecture that executes a single instruction stream, but yet it has more than one arithmetic logic unit in this case, okay? We have 1, 2. And the control unit also generates the control signals from all the arithmetic logic units, which executes the same operation on different sets of data items, okay? And then we have the multiple instruction string, multiple data string, okay? Where we have, okay, that's where we have something like this. Then we have control, and operate. Then we have another control, and then we have another operate, right? So we have the instruction here, then we have the data, and then we have the result, we have the instruction here, we have the data, and then we have the result. So this is instruction, data, result. This is instruction, this is data, and this is result, right? And then we have this linking up with this, and this linking up with this, and then we have the memory, right? So this is more like multiple processors, right? So it consists of more than one independent processor, and each can execute a different set of instructions. So hence multiple instruction stream on its own set of data also. So this on this, this on this. So we have multiple data stream. Why the multiple instruction stream, single data stream? There, logically, machines of that type will execute different programs on the same data item, and the practical implementation, you know, still being queried anyway. Okay, now we already know that the computer architecture is the programmer's view of the computer, usually referred to as the instruction set architecture. So it defines the instruction set. The instruction set architecture defines the instruction set, which is the language, and also the operand location. Operand location, which happen to be the registers and memory. That's what the ISA does. So examples of computer architecture I think somebody mentioned RISC, right? You guys have really done a lot on the reduced instruction. Excuse me. Okay. Reduce instruction. Okay. Set computing microprocessor. This is RISC. Okay, now we also have other types of processors, microprocessors. Okay, this is a microprocessor. We have other types, the complex instruction set computing, the CISC. We have the application-specific integrated circuit, that's ASIC. Then we also have the DSPs, okay, digital signal processing. And we also have the EPIC. I think that's explicitly parallel instruction computing. Yeah, explicitly parallel. Yeah, explicitly parallel instruction computing. Okay, so these are all types of microprocessors. And then we now come to examples, you know, of the architecture based on RISC, based on reduced instruction set computing. So that is where we have, let's wipe this. So we say architecture based on RISC. We have the ARM, which is Archon RISC machine, or some call it advanced RISC machine. Okay, well, though they are very weak, but low power processors, you know, for simultaneous and for smartphones and all of that rather. Then we have the x86, okay? And then we have the MIPX. This is from ATX86 microprocessors. For this MIPS, which is microprocessor without interlocked pipeline stage or stages, right? Then we also have SPARC. That's scalable processor architecture. We also have Power PC, performance optimized with enhanced RISC, and so on, okay? And so on. There are so many, you know, quite a number of examples of the computer architecture based on RISC. So, the point here is that the instruction set architecture acts as the interface between the software and the hardware components, okay? So we have the software, and then we have the hardware. And that part that, you know, is in between is the instruction set architecture. So now I'll say that the instruction set architecture describes the basic components required by a computer programmer in order to program a computer, okay? So the ISA describes some basic things. Number one, the supported data type. And two, the possible states. That is the main memory or register. Okay, we'll talk about the main memory or the register. Then also their semantics. That is memory consistency and addressing modes, okay? Talk about memory consistency and addressing mode, which you already know, right? And then we now talk about the instruction set, the instruction set. Here we talk about well, the instruction set is a set of machine instructions that comprises a computer machine language, okay? And then the last point here under ISA is the input-output model, okay? The input-output model. So it should be noted that all programs running on a computer use the same instruction set. For instance, your word processing, your spreadsheet, and so on, then are compiled into a series of simple instructions such as add, subtract, branch, and the likes. So computer instructions indicate both the operation to perform and the operand to use itself. So the operand may come from the memory or the register, and it could also come from the instruction set itself. So speaking in simple terms, instructions are encoded in machine language, okay? Zeros and ones. And the programmers represent these instructions in a symbolic format called the assembly language, right? I know you already covered the assembly language. So microprocessors are now the digital systems that read and execute machine language instructions. That's what it is, okay? And for instance, the ARM we talked about represents each instruction as a 32-bit word, right? So for ARM, each instruction is represented using a 32-bit word. The MIPX, they use both 32 and 64-bit word. You know, the x86 architecture represents each instruction as a 16-bit, 32-bit, and 64-bit word, right? Just like that. Okay, and we know coming from looking back, or better still, let's reflect now on the abstraction level. We see that the microarchitecture is the specific arrangement of registers, memories, the arithmetic logic unit, and other building blocks to form a microprocessor. So looking at what we are now going to be doing going forward, you see that the programmer uses the high-level language to develop the application programs. Then a compiler is used to convert the high-level language into the assembly language. And then the assembly language, or the assembler rather, is used to convert the assembly language to the machine language, which is in bits, right? The machine language. Now, so looking at what we just said, we see that the instruction set architecture, ISA, sits on the computer. And then we now have other applications like your Word, your Windows, even your C++, and so on, okay? So all programs has to be converted to the instruction set by the computer, okay? All programs. And the instruction set of a computer is the language the computer can interpret. So all programs are first translated to the computer's instruction set before they can be run on the underlying machine, which is the computer. So it flows in this way, in this pattern. And the instruction set of a computer associated with the organization of the CPU, the central processing unit of the computer. So it should be noted that each computer has a unique instruction set associated with it. And the instruction set is composed of individual primitive instructions that instructs the hardware of the computer to specify a primitive task, such as, say, moving a content of a memory location to, say, a register within the CPU, or better still, adding the contents of two CPU registers, okay? And now we are going to be considering some examples of instruction set architecture. And here we have the accumulator-based, ISA, and the register-based ISA. Okay. Well, okay. With the look of things, we may have to have another class, right? But let's see how far we can go. So, so let's look at the accumulator based. So we have the control unit. Then we have the memory buffer register. Then we have the memory address register. Then
I have a lot to do during this
accumulator.
The work is
And then we have the arithmetic logic unit. So this now is related to this. Then this connected to this. And this to this. Then this goes out, and then this goes out. So all right, don't mind the irregular lines, okay? So just to serve the purpose. So here we have, this leads to the data bus, while this leads to the address bus. And then let's just have the, this is the accumulator base, right? Yes. Then let's have the, this accumulator base ISA, the register base. So we also have the control unit here. Then we have registers. This is R1, register 1, register 2, all the way to register Rn plus 1. So these are the lines linking the arithmetic logic units. So we have this connected to this. We have the control unit that way. And then this now connected to this. Right? Then so this now is the register-based ISA. Okay. So I'll just run through this, and you see that for the accumulator-based, that is for this accumulator-based instruction set, instructions addresses the question of which part of the CPU and or the memory a user can access in the software. So you should know that the memory itself is a passive unit used strictly for information storage. So it is used to hold both instruction and data. So any processing, in other words, any processing is done outside the memory. So CPU contains temporary storage elements called the register, right? Now, in the accumulator-based instruction set architecture, the user has control over only one storage in the one storage register, which is the accumulator in the CPU. So in order to process data, the data must be presented in this special register called the accumulator. So the type of instructions the instruction set designer chooses is based on the functionality desired as well as the underlying architecture, okay? So here we have just one register, which is the accumulator. But in the register base, we have multiple registers. That's a major difference, okay? Now, the accumulator register actually serves as both a source and a destination for both the ALU inputs, okay? Because you see it, it goes in and comes out, yeah. And here, we have the memory buffer register, and it is used to hold information as a buffer between the CPU and the memory, okay? And now, in this organization of the CPU, all traffic instructions and data between the CPU and the memory is temporarily stored in the memory buffer register, which is connected to the data bus, as seen here, of the CPU. So this data bus is the data bus of the CPU, connected to the CPU, linking the CPU rather. So the data bus connects the CPU to the outside memory. So it is actually bidirectional. So when we talk about the organization, you see all of those though. So that is used to move data in and out of the CPU. Now you also see that the memory address register interfaces via the address bus. So it contains the address of an instruction or data found outside the CPU, that is in the memory, let's say in the memory. So the address bus contents are found in the register MAR. So the data to be read or written is placed in the memory address register. So for the accumulator-based instructions, these are instructions used for communication between the outside and the hardware of the computer. So programs written in high-level language must first be translated into the instruction set of the underlying computer before it can be executed. And some of the examples of the accumulator-based instructions are, let's change this color. We have load and store instruction. We have the arithmetic and logic instruction. Let's put it that way. Then we have the register transfer language. Okay. So when we talk about the load and store, for instance, a load instruction directs memory to place the content of a word on the data bus, right? Now, a store instruction is used to store the value of the accumulator into the memory base at that memory location. So let's assume we have LOD 101. So you see that it has two parts. The operation part, this is the operation part. And then we have the address part, right? This part is the address part. So when the instruction is executed, the contents of memory at address 101 are loaded into the accumulator. Same thing for STO 101, for instance. So it will store a value of the accumulator into the memory word at memory location 101. So to read a specific word in memory, its location must be specified. And this has to do with the addressing methods we mentioned earlier, okay? And then same for the arithmetic logic instruction. So for the arithmetic and logic instruction, the power of a computer is attributed to both its ability to store information and process it at high speed. Okay, so this helps in performing operations. And then we have instructions like add, subtract, and, or, and the likes. Okay. So the register transfer language specifies the source or destination of information transfer, which could either be the register or memory contents. Okay. And then we now have the general register-based architecture. So I already mentioned it, that the major difference is that we have multiple registers here, unlike the accumulator base that we have just one register, which is the accumulator. So in the general register-based architecture, which is CPU organization actually, the CPU contains many registers that are directly accessible by the users through the provided instruction set. Okay, so this reduces CPU memory traffic, unlike in the accumulator-based I. Okay, and there you see register R1 all through to Rn+1 are used to replace the accumulator. So in the accumulator-based architecture, the user cannot access other registers in the CPU outside of the accumulator registers defined by the instruction set. So that the process of moving information in and out of memory is quite expensive in terms of speed, as memory access is slower than the CPU execution time in terms of the accumulator based system. Okay, so I think I thought to just put this through to this point. So we are really running out of time. You guys need to go for your spot. So what we are going to do now is we are going to have another class probably after our quiz. Okay, and there we'll talk about machine instruction, representation of data, and then computer organization, and also see if we could play with one or two examples using the hardware description language. Okay, so I think for now this is a good place to stop. So any question, please?
Thank you, sir. Sir, for the quiz, what is the format going to be like, sir?
Well, the format for the quiz is going to be examination format. So we call it mid-semester examination. Okay.
Will it be virtual or physical, sir?
No, it's going to be physical. We are going to take physical exam. So we're going to be writing and doing a one or two analysis and the likes. Is that okay?
Yes, sir, that's fine, sir. And sir, can we get AOC, sir?
Olayinka, you have nothing to worry about, okay? Well, let's see if we'll be able to just remind me, okay? Let's see if we'll have a brief introduction, maybe for 10 minutes on Zoom. Next week be lecture free, since next week is convocation. So if it's going to be lecture free, we could still, probably 20-30 minutes online, so we could address some of your concerns as far as the mid-semester examination may be concerned. Is that okay?
Yes, that would be great, sir. Thank you.
Okay. So the class rep will have to remind me, okay? So if that's it for now, so do have a nice day and bye for now.